whatever you want. It really is an artifact. You have an interfacial transition zone. Basically, I'll give you the simple theory of it. If you have an aggregate particle, I told you what will preferentially precipitate on the aggregate particles? Calcium hydroxide. What's the shape of calcium hydroxide? Hexagon. When you put a bunch of hexagons together, are you going to fill the space completely? Basically, what will you have then? You will have interlayer space there. And then calcium hydroxide, if you look at the previous picture, you will also see another interesting thing. What is forming first in this system? Calcium hydroxide and yttrium. Both of them are crystalline products. When you put different crystals together, you leave a lot of space in between the crystals, not like amorphous products, right? So, what is formed initially are both crystalline products. Both crystalline products love surfaces. They go stick to surfaces. Surfaces typically are aggregate surfaces, sand surfaces. When they go and stick on sand surfaces, then the corresponding CSH that's forming will have to form in the remaining space. Naturally, very close to the aggregates, you will have more porosity. You don't have to create a new theory for it, like a lot of people do. Right? A lot of people come up with a lot of crazy theories of why there is interfacial transition zone. About 10, 15, maybe 15, 20 years ago, ITC was a big question of debate. It's very simple. If you think of nucleation, nucleation needs surfaces, sand particles are surfaces, crystalline materials precipitate first. Of course, there has to be porosity. Right? That's what is happening. And so you will have interfacial transition zones. There's a way to reduce interfacial transition zones. There's a way to make the ITCs more denser. It's by typically putting materials like silica. Common sense. Tell me why would silica fume densify the interfacial transition zone? Not just consume CH. Even more important, what is formed first? CH. As soon as CS calcium hydroxide is formed, silica fume is there already. It will immediately consume that CH, and you will form CSH very quickly, right? So there is an immediate transformation. So these things can't go and lie on sand particles and create porosity. CSH is formed there, which is amorphous and fills in all the pores straight away and quick. And that is why silica fume densifies the interfacial transition zone. The advantage of densifying the zone is that your moisture and ionic transport will be much slower. Right? You can get your corrosion will be delayed. All the other durability issues will be delayed. Higher water cement ratio results in larger CH, ettringite closer to aggregates, poorly crystallized CSH and smaller crystals fill some of those voids. Okay. Now we will get into characterization, pore structure characterization at the cement paste level. We'll do more of the concrete level later. So a lot of people have questions on how do I quantify it, how do I identify it. Some techniques, I'll show more techniques tomorrow and day after. I don't want to overwhelm you with everything in one day, but we'll go slowly, we'll do more later. So, quantification of two things are important in cement paste, in cementitious materials. You have to quantify the hydration products because the filling of the space is what gives you all the products. So you want to quantify hydration products. But you want to quantify the pore space also because pore structure is what causes all the problems. Right? All the durability problems are caused by pore spaces. Like I said, you may have a certain porosity that's no guarantee of good durability or bad durability. It depends on how tortuous, how connected the pore sizes are. Especially when you have chlorides, and there are a lot of complicated things associated with it. Sometimes both hydration product quantification and pore structure quantification in combination will have to be done. Classic example being corrosion. You need the pore structure because chlorides are going through the pore structure. So you have to quantify the pore structure to find out how the chlorides are going to get to the reinforcing steel. But while the chlorides are going through, and if you have aluminates in your system, what will happen? Chlorides and aluminates will react to form Friedel salt. Have you heard of Friedel salt? Chloroaluminates of Friedel salt. Friedel salt will start depositing in the structure, so then you have to quantify how much of Friedel salt is there to really understand how much of delay in corrosion you can get. Right? So all these are very interconnected set of things. So I'll give you a few topics that that we look at. Image analysis, I'll do some initial ones, and I'll do more image analysis I think later. But this one we'll do a few techniques. Some of those techniques are easy, some of them are a little more complicated. So gas absorption has been an old technique. It's been there for quite some time. Water vapor and gases interact with solid surfaces. Cement paste is an ideal absorbent because cement paste has a lot of voids. Paste-water interaction is a reversible thermodynamic process, which means water molecules that are adsorbed can be released without losing any mass. So it's a totally reversible process. The assumptions are not completely valid, but you can use it for this idea. So BET absorptions, Brunner, Emmett, and Teller, a very common microstructural characterization technique. It's an extension of a Langmuir theory where the adsorption of molecules is related to gas pressure or a concentration of a medium above the solid surface at a fixed temperature. Remember Boyle's law and Charles' law from your physics or chemistry classes a long time ago? It's a variant of that. It's an extension of that. It's very simple. It's not as complicated as you think. If I apply a pressure, basically what I'm saying is, this is a method to find out how much is the surface area of the solids. So if I have a hydration product, how much is the solid surface area of a hydration product? Remember, solid surface area of the products, well, solid surface area of hydration product or for cement. I told you, surface area of cement is important for reactivity. And in the morning we explained why that's important, right? So if you have a certain surface area, and remember, this is not a surface area like you put in a carpet here that I can go and measure. This is surface area in 3 dimensions. Can you conceptualize this? This is all this twined, this is like, you put all these things for birthdays, you hang all this twisted paper and stuff, right? You try to take all of this, bundle it, put it in a box, and ask somebody to find the surface area. That's exactly the problem here, right? So, how will you do? You can say, oh, I'll take it out and spread it out and then measure it. Can we do it for cement? So you have to, this is in space, I have to go in with something, I have to squeeze something in that is smaller than the layers, and then I have to find out a way where I can spread one molecule of what I am pushing in into the surface of all of those. And once I know, I'm sure that all these layers are covered with one molecule each, I can find out how much of molecules I have sent out, and therefore I can find the surface area. See how complicated it is? And that's a method. Which gas do we use? We don't want it to be interacting with cement paste. What gas do we use? Huh? Nitrogen. If you don't want to react with anything, you use nitrogen. So B is surface area is nitrogen. Nitrogen is good because the size of the nitrogen molecules are also much lower than the size of the particles that you're interrogating, right? So you're sending in nitrogen into this complicated structure and expecting nitrogen to stick onto the surfaces, and you apply a pressure and you find out when you don't have to apply any more pressure, you know nitrogen has completely covered the surfaces, you know how much pressure you have to apply, you know how much of quantity of nitrogen you send, you back calculate, I have that at the surface area. Right? Because at the end of the day, surface area is what dictates durability. If you have more surface area of cement paste available for deleterious materials to react, you have more problems, right? So surface area characterization becomes very important. So is the idea clear? I've just put in one simple picture to show what that means, but I've explained to you the complicated sequence. Okay, so basically, number of molecules needed to form the monolayer is determined. If I have this convoluted pieces inside a box, I'm trying to find out how many nitrogen atoms or molecules are required to form one layer on top of the reaction product that I want to determine the surface area of. All of you good with this? Get the idea? That's what we are trying to do. So, there are many assumptions. All the sites are supposed to be similar, which basically I'm saying that if it is CSH, I am assuming all CSH in this to be same, all calcium to silica ratio of say 1.2 to be constant throughout, absolutely no change. So I can't afford to make any more assumptions. It's already so complicated. I also assume that heat of absorption of second and higher layers is equal to heat of liquefaction. So what is my guarantee that there is only one layer of nitrogen? How can I guarantee that nitrogen goes and stays only one layer? What happens if 2, 3, 4 layers of nitrogen happens, right? Then I will have to find out a way to account for the secondary layers of it. Okay, so here is the equation to account for that part. I'm assuming that heat of absorption is equal to heat of liquefaction, or the rate of condensation on the surface is equal to the rate of evaporation, and therefore I come up with a complicated equation which takes the volume of gas absorbed, monolayer capacity, saturation pressure, all of that. But then I simply plot a curve of partial pressure. Basically you're plotting the vapor pressure, which is the pressure that you apply to put nitrogen into the system, to the saturation vapor pressure, and I'm plotting that as a function of volume of gas that I have pumped in. That you can always measure. You can have a meter at the end of the tube and you can measure how much of volume of gas has gone, and that as a function of pressure, and that gives me a curve like this. Okay, and I say that, and I make some assumptions here. Where is that? Okay. I make an assumption here saying that between 0.05 partial pressure, somewhere here, and between 0.35 of partial pressure, this line is linear. Okay, and you will get that. After that, I don't know what is happening. After that, all what is happening, I associate it with multiple layers of nitrogen gas on the surface. So 0.05 to 0.35, you consider it to be the monolayer absorption. You take that slope of this part between 0.05 and 0.35, and then you use this equation to find the specific surface area using Avogadro's number, molar volume, etc. So between 0.05 and 0.35. Less than that, it underestimates. More than that, it overestimates. You don't want to do that. So that's a simple way to do specific surface area. VET instruments should be available in many material characterization labs. Anybody who deals with any powders, any kind of powder, uses this method for specific surface area. So you can hydrate a cement paste. You can just powder it nicely, give it to them. You can find the specific surface area, and you will know that you put in 25% fly ash, you put in 30% fly ash, you put in 50% fly ash, very quickly you will find out how much fly ash is there in the system. So if you want to know how much of, so for example, somebody tells you, I want a clinker factor of 80%, and somebody gave you a concrete with only 50%. Right? So if you hydrate at exactly the same for exactly the same time and compare those, you will know which one has a higher reaction product and which one has a OPC, CSH products will typically have a much higher surface area than unreacted fly ash. Now, if the fly ash also reacts and forms secondary CSH, it becomes very difficult. But early age, before 28 days, if you want to figure out how much is there a difference in cement content, this way can be. Okay, the next one is the Kelvin equation. This is simplistic, more simplistic. It relates the cylindrical size of the pore to the pressure at which condensation occurs inside the fluid. If you have an air conditioner working, you see the fluid dripping out of condensate from the air conditioner, right? You see in cars, you see in buildings. Why is that happening? What causes condensation? What is the primary cause of condensation? What is condensation? Change of phase from gas to liquid. Condensation is gas to liquid. So you are in a gaseous phase. So what you can think of is a cylindrical pore where you have a liquid and a gas, right? So it is an partially saturated pore which you have in concrete all the time. You have solid and the liquid. Now if you apply a relative humidity difference, so if the pore is at relative humidity of say 80%, you apply a relative humidity difference, you drop it down to 10% like I said earlier. What will happen? Water will evaporate to gas. But if you immediately jack the relative humidity back up, that gas will condensate. Right? So by partial pressure variation, you can condensate in partially saturated systems, you can condensate the liquid. So cylindrical pore to the partial pressure, if that happens, with increase in pressure, thickness of the water or whatever is that you're supplying, thickness of the layer on the pore walls increases. Condensation occurs in smaller pores first and then happens in larger pores. Therefore, you can use this simple Kelvin equation. It's nothing but surface tension, volume, the contact angle, the gas constant, temperature, partial pressure. We can use this equation to find out the radius of the pore in which condensation occurs, and then if the pore that condensation occurs is really small, then you know your concrete has a much fine pore structure. For example, if you have a fly ash, you hydrate it for 90 days, you will find the R value to be much lower than in an OPC system. Right? Because of pore size in fly ashes, that's why we use second supplementary sintering materials, right? Not just for strength, but to reduce or refine the pore size. So this is a way to quantify pore size. And again, not easy to do the measurement. So you see how complicated we are dealing with individual atoms in a really small size sample. So the error, the chances of error are high. The sophistication that you need in the equipment is high. But the advantage is you can quantify things at a very small subtle level, which you otherwise cannot quantify. So another way to find out if pore refinement has indeed happened. These are all, again, I'm doing this in the order of evolution of these techniques. You really don't need, again, I just gave you the theory for this so that we are all aware of it. But to really find out what the pore sizes are, we really don't need technique. Now we have mercury intrusion velocity at MIT, which we can do better. But these are all the precursors to those techniques. And we'll get to MIP. That's absorbed layer thickness. Pore radius calculated by Kelvin is smaller than true radius, but that you correct for by this parameter. There is a model-less pore method. All of these assume cylindrical pores, and somebody comes and tells you, who told you there are cylindrical pores in concrete, right? Who told you the pores in concrete are cylindrical? Good question. They're not cylindrical. They're random shape. But then, by the same argument, you can ask me, who told you the cement particles are spherical, right? But if you look at any computer model, they'll consider cement particles to be spherical. The sphere is the size that we can computationally handle. Angular particles becomes extremely expensive computationally. If I have to engage a supercomputer for 6 days to find out hydration of 1 centimeter cube of cement, it's not worth it. Right? These models have to be run faster if I have to make realistic calculations. And if more people have to use it, these models have to be faster. If you give very complicated models, nobody will use. That's why we need to simplify. But again, in our business, we oversimplify with some custom compressive strength. That's the price that we are paying now sometimes for oversimplification. Because the whole idea was, oh, the guy in the field should know. The guy in the field should know, yes. And you are not going to teach him cement chemistry for sure. But the technique that he uses should be relatable to what you have used to design that material, right? If you can tweak it whichever way you want, then we will end up with all the quality control problems that we have. We'll end up with all the, field is doing one thing, lab is doing one thing. There's always fight between the contractor and the engineer and the client. I designed for, the concrete supplier says I designed for 40, I got 40 in my lab. the concrete contractor will say, no, you get only 30. The engineer will say, oh, I asked for 50. We keep on fighting for it, and then nothing will happen. But this is where some disconnect will happen. I'll skip this. We'll go to MIT. How many of you have used mercury porosimetry in any of their work? Nobody. Have you seen this instrument? Have you heard about this? No. So this is a very useful, we will go through this and talk about what is good and what is bad. It's a very useful instrument for a lot of purposes. It's a very common post-structure characterization technique. It has its own drawbacks, a large number of drawbacks, but it is among a very useful technique for porosities and some kind of pore sizes. Okay?